Hi there. Now we're looking at part C of question 16 of 2015 HSC mathematics paper. The diagram shows a cylinder of radius x and height y, inscribed in a cone of radius r and height h, where r and h are constants. Basically what they are trying to say is we've been given a cone with the height of h and with the radius of r at the base, and then you want to see if we want to fit a cylinder inside that, what could be the possible size for that cylinder? All the possible sizes. Alright, the question goes like that. In part I, show that the volume V of the cylinder can be written as this expression. Okay, so V is equal to h, which is the height of the cone, over r, which is the radius of the base of the cone, times by pi x squared. X is the radius of this cylinder that we are fitting inside. That's x. Pi x squared times by r minus x. That is the first part. So we are trying to find the volume of the cylinder. But as you can see, it is only in terms of x, but you know that the volume of the cylinder involves also its height, which is in this case, they've given it as y. So in other words, we should find a way of expressing y in terms of x, because your answer is only in terms of x. To do that, we might look at this triangle, or these two triangles. This is one triangle, and this is this smaller triangle inside that. Okay, this is one triangle, and maybe I give them names. So A, B, C, D, and E. Alright, so we have these two triangles and they are similar. Okay, so the two triangles are similar because DC and EB are both vertical lines, and you know that this is like 90, this is 90, they share this angle. So we say that consider triangles CDA or ACD, which is the same thing, and triangle ABE. They are similar. Why? As we have DC parallel to BE, both vertical lines, and so that means that your angle B is equal to angle C angle D is equal to angle E. Okay, you can be a bit more specific, maybe rather than writing just B, it would have been better if I wrote it as EBA, and rather than writing C, A, C, D, and rather than writing D, C, D, A, and in place of E, B, E, A. I could have written that, that would have probably would have been more accurate. Alright, why is that? Because they are corresponding angles. Corresponding angles. Okay, so that means that two triangles are similar. Triangle ACD is similar to triangle ABE, and because two angles are equal, then equiangle. You don't need to do the third one, because the third one will be automatically equal. Okay, you probably can write it in a better arrangement, so in a more convincing way, but that is the reason for that. Now they are similar, so we can write that y over CD is the same as AB over AC. And the reason is corresponding sides. Sides of similar triangle. Alright, CD is h, so we got y over h is equal to AB. AB is this radius, take away this, which is x. So radius take away x, AB, radius of the cone, take away x, base of the cone, take away x, and AC is the whole radius of the cone. From here you cross multiply and you find y, so you get yr is equal to h r minus x, and divide both sides by r, you get h r minus x over r. So we find y in terms of x. Alright, but we have the volume of the cylinder. Volume of the cylinder is pi times radius squared times h for a cylinder. That's the formula for a cylinder. They are given it in the question answer. Now, my r is x, so x squared, and my h is y, which I just find. So y, which I can write pi x squared times by h r minus x over r. Okay, this should be what they have asked from us. Yes. So we can rearrange it a bit to write it in the way that they are written. So h on r, pi x squared times by this bracket. Okay, that answers the question, the part I of this question. Part I. For part II, they are cylinder will never exceed 4/9 of the volume of the cone. So in other words, you can fit many different cylinders as long as its base is on the base of that, and you can make it wider, but you lose on the height. Alright? So there is an optimal point where you have the maximum volume, and you want to find that maximum volume and show that it is not going to be greater than 4. Okay, basically you know that to find the maximum of any quantity, we need to differentiate and equate the derivative to 0. So let's do that here. So V is equal to h on r pi x squared r minus x. What I'm going to do, I'm going to take this bit as my coefficient because it's a constant value, and just differentiate the rest, which is that bit, x squared times r minus. So I'm going to say h pi on r, then I'm differentiating this bit with respect to x. Okay, this is the product of two functions, or maybe it's easier if I expand it. So I get v dash is equal to h pi r d over dx. I'm just expanding that, rx squared minus x cubed. Alright, so that becomes v squared. I don't need to use the product rule anymore. So h pi r, derivative of times by the derivative of that. R is a constant, stays, and derivative of x squared is 2x. So you get 2xr or 2rx minus derivative of x cubed is 3x squared. That's our derivative. You can put it equal to 0 to find any possible maximum or minimum point. So letting it equal to 0 will give us that. So dividing both sides by this is a constant, h pi on r, so you get 0 is equal to 2rx minus 3x squared. Now factorizing for x gives me 2r minus 3x. Okay, for this to be equal to 0, either of these components must be 0, either x or this bracket. So x is equal to 0 or the bracket is equal to 0. From this equal to 0, you get 2r is equal to 3x and x is equal to 2r on 3. 2r on 3. Okay, here we say that x equal to 0 has no meaning because if x is equal to 0, basically you're saying that your radius of cylinder is 0, which we have no cylinder. So if x is equal to 0, there will be no cylinder. No cylinder. So it means that you're not going to have nothing to discuss. But for the other one, obviously we are going to have a cylinder which is x is equal to 2/3 of the radius of the base of the cone. Okay, the only thing is that could be the maximum value, but we got to check it. To check to see if it is maximum or minimum, we go to the second derivative. I write this first derivative that we got, and I differentiate it again to go to the second derivative. So we have v dash is equal to h pi on r times 2rx minus 3x squared. To differentiate it again this is a constant, I'm just keeping it and times it. I differentiate inside, 2rx, remember that 2r is a constant, so it becomes 2r minus, that becomes 2 times 3, 6, 6x. Alright, we are trying to see that this x value is giving a maximum or minimum value. To be a maximum, this should give a negative value for second derivative. This x value, when I sub here, should give me a negative value for v double dash. So let's do it. So pi h on r, so I'm just writing this, 2r minus 6, and the x is 2r on 3. So that gives me v double dash pi h r times 2r minus 6 times 2 is 12, divided by 3 is 4. 4r, that is negative 2r. So it becomes negative pi h r times 2r. And this r cancels out, so it becomes minus 2 pi h, which is a negative value because h is positive, as h is a length and length cannot be negative. Alright, so we have a negative value for second derivative. When you got negative value for second derivative, it means that you have a maximum, because that means it's concave down, and when you got concave down, then you have a maximum. That's the reason. Okay, now we know that this value of x is providing us with the maximum volume. We sub in the expression for volume to find that maximum volume. So v is equal to this. I'm just sub in for x using this value. So v is equal to h on r pi times x squared, which is 2r on 3 squared, times r minus 2r on 3. So v is equal to h on r pi times, that becomes 4r squared, I'm squaring the top and squaring the bottom, times r minus 2/3 of r is just 1/3 of r, or r on 3. So that gives us, this r will go away with this r, and it gives us h pi times 4r squared on 9 times this r and this r are gone, 1/3 here. Okay, and I'm rearranging this a tiny bit. I'm just bringing 4 9s in the front, so then you get pi, you get h, and you get maybe I can put also 1/3 at the front. So 4 on 9 times 1/3 times pi h r squared. Okay, I wrote everything just in this order because I want to prove that point, that this volume is 4 9s of the volume of the cone. And we know that this is the volume of the cone, because the volume of the cone is 1/3 pi times r squared times h. Okay, so you can say as as 1/3 pi r squared h is the volume of the cone, capital H, volume of the cone. So the maximum value for the volume of the cylinder is is 4/9 of volume of the. Alright, that concludes this question as well. Thank you for watching.